We're going to begin talking a bit about polar coordinates. Now, in Calculus 2, this should be review. We have some common equations which we can use to relate polar coordinates to Cartesian coordinates, meaning r and theta to x and y. So when we think about a polar or graphing a point in the polar plane, we're always going to have an initial side and then a terminal side. We have a direction or rotation measured by theta, and then we have a directed distance r. R can be positive or r can be negative. And the point here at the end, we call that point r theta. So we have a radius and then a rotation. And that point, what you see over here when we look at this standard way that we present polar data or ordered pairs and relate them to Cartesian XY data, again, that's r and theta are showing up, but I want you to notice we have an x and a y in there. Okay? So thinking about some trig and looking at this picture, if we thought about that as being a triangle with a hypotenuse r, one relationship that we could make if we thought about sine, and we remember that sine is opposite over hypotenuse, that would be y over r. And if I rearrange that, multiply by the r, I have r sine theta equals y, which you can see right here in my equation, which relates polar and Cartesian coordinates. And by a very similar argument, we create the x equals r cosine theta equation. Of course, r squared plus x squared equals y squared. That could also be rewritten as x squared plus y squared, if I square root that, equals r. Okay, so we can rearrange these in different ways, but the main idea here is we understand where a polar point is located on a graph, and then we have these equations that relate x and y to r and theta. Here we have a table of equations, and I want you to notice we have some Cartesian equations, x and y, so a line, a vertical line, a rational equation, that would be a hyperbola. This should also represent a hyperbola, just in a different form. And as you start to look down here, I'm not exactly sure what the shape of that Cartesian equivalent is, but you'll notice the polar equation equals r equals 1 minus cosine theta. That looks like a cardioid to me. It's presented much more simply in polar notation than it is in the XY Cartesian notation. So polar notation, we need to understand it and know how to convert between XY Cartesian equations and r theta polar equations. So let's do an example. In this example, we're going to convert this polar equation into a Cartesian equation. Here we have r squared equals 4r times cosine theta. So being able to convert this hinges on knowing those identities we established at the start of this video. So looking at this, remember, I know that r cosine theta equals something. That is something I know. X is equal to r cosine theta. And I also know that r squared equals x squared plus y squared. So by performing these two substitutions, x squared plus y squared is now equal to 4 times x. So I have eliminated r and theta, and I only have x and y in my equation. And if we wanted to determine what this is, well, we know this is a conic. We have x squared plus y squared So it's either an ellipse or a circle, and since the coefficients on both of those are the same, it's a circle. Putting that into standard form would be x squared minus 4x. We're going to need to determine some value, plus y squared equals 0. And whatever value I add on the left, I'm also going to need to add on the right. So if we think about completing the square, and we take that b value for this expression, b divided by 2 squared, that would be negative 4 divided by 2 squared, which is negative 2 squared, or 4. And since I add 4 to the left, I also add 4 to the right. What I have just written there, that factors to x minus 2 quantity squared plus y squared equals 4. So this is a circle of radius 2, and that radius is coming from this, x squared plus y squared equals r squared. So my radius is 2, and it is centered at positive 2, 0. So in this example, we converted r squared equals 4r cosine theta into this Cartesian equation. Let's do one more example. Here we have a polar equation, and we are going to convert it to its Cartesian form. We're going to start with r equals 2 cosine theta plus 2 sine theta. Now we want to remember our polar to Cartesian identities, but if you don't have them all perfectly memorized, you can always think about drawing a right triangle. So we have theta, x, y, and r. And if we wanted to relate some of these variables using right triangle trig, we could say that cosine theta, remember cosine is adjacent over hypotenuse, so x over r. And the same for sine, but sine theta would be opposite over hypotenuse, y over r. So in this case, we now have r equals 2. Cosine theta is x over r plus 2. Sine theta is y over r. So in this case, since I now have fractions or rational expressions, we can multiply by the LCD to clear the fractions, which would be multiplying everything in this equation, multiply both sides by r. And if I do that, that gives me r squared equals 2x plus 2y. So that, now I know what r squared is equal to. R squared is equal to x squared plus y squared. So plugging this in, we have x squared plus y squared equals 2x plus 2y. At this point, we have eliminated r and theta. We just want to clean it up, maybe put it into standard form. So this is the same as x squared minus 2x plus y squared minus 2y equals 0. And in order to put it into a meaningful standard form, we complete the square twice for both of these values. So x squared minus 2x, I would need to say negative 2 divided by 2 is negative 1 squared, would be plus 1 plus y squared minus 2y. Again, we would add 1 here. And since I added 1 twice on the left, I have to add 1 twice on the right. 1 plus 1 is 2. So what I just did was completed the square, so I can write these, I can factor them, and I get a perfect square binomial. So that would be x minus 1 quantity squared plus y minus 1, quantity squared, equals 2. So this is a circle of radius square root of 2, and the center is at positive 1, 1. And that's it. And like I said, you should have had some practice previously with this in your trigonometry class.